Welcome to part 2, where we'll explore the slopes of a secant line and the slope of a tangent line. And we will explore what the heck a secant line and a tangent line is as well. Let's take a look back at the fruit fly example from part 1. We can see that the fruit fly population increases over these amount of days, and that is shown in the blue curvy function here. And then we found the average rate of change between point P and point Q between day 23 and day 45. We found it was about 8.6 flies per day. This black line right here that connects point P and point Q, the one whose slope was the average rate of change, this is a secant line. Some people say secant or secant. It does not have anything to do with the trigonometric function secant. It is different. And so this line right here is a secant line. A secant line is a line that passes through 2 points on the curve. When we say the curve, we mean the function in question. Here, this blue function f of x. So a secant line is one that hits and passes through 2 points on the curve, aka the function in question. And so that's why this line right here is called a secant line. And the slope of the secant line, what we found was 8.6. That is the average rate of change between those 2 points. And we know that slope is denoted with a italicized lowercase m, and so the slope of a secant line we will see identified as that m with a subscript sec for secant. The slope of the secant line, once more, represents the average rate of change between those 2 points that it passes through. So if you're asked to find the slope of a secant line, it means asked to find the average rate of change. So what we've done is we have found the average rate of change between day 23 and day 45 was about 8.6 flies per day. That is a pre-calculus idea, finding the slope of a line. And when I say pre-calculus, I mean before calculus. You most likely learned how to find slope between 2 points in 7th or 8th grade, and you've been doing it since. But what if we wanted to find the slope not between 2 points on the line, but find the slope at exactly 1 instant? That's a calculus idea. Let's think about what that means. We can clearly see that this average rate of change doesn't really describe what's happening at day 23, nor does it describe what's happening at day 45. At day 23, the fruit fly population is increasing rapidly. If we were to draw a line here, like this, it would have a much steeper slope. Whereas here at day 45 at point Q, the fruit fly population is not increasing as rapidly. In fact, it's pretty much leveling off. It's basically stopped increasing. This line here would almost be horizontal. It would have a slope of 0. And so this line, if we extended it, doesn't really do a good job of telling us what's happening at an exact time, on an exact day. And so what we're going to do now is we're going to attempt to find how the fruit fly population is changing on exactly day 23 here at point P. What I'm going to do is draw a few more secant lines and move point Q closer and closer to P. Let's see what happens. All right, so we've already established this first one, the slope between P and Q here, where Q is 45, 340. So I'm not going to show the work for that one. We've already established that that's 8.6, and that is flies per day. I don't have a ton of room, so the F is going to stand for flies. Let's bring Q a little bit closer to P, though. Let's bring a new Q here at this point. Right here, and I don't know every single exact point, so I'm going to be estimating a little bit. I do know that this is 40, and I actually am just going to write it down here. I know that this is 40, comma, it looks like we're a little bit under 340, so I'm just going to go with 330. All right, let's take a look at what that secant line would look like. If we are going to draw the secant line now between P and this new pink Q, it would look just like that. It's not perfectly through the Q, but I'm pretty happy with that based on what I'm doing on my iPad here. All right, let's find the slope of that line between the coordinate point P and this new Q right here with this coordinate. I'm going to do this work off to the side because I don't have a ton of room right here. So I'm going to do this work over here. So to find this new secant, slope of the secant line, I'm going to do our y, 330, minus our y, 150, divided by the x, 40, minus the other x, 23. And again, this is the work that should go right here in order to find the slope. And let's see what we get. 330 minus 150 equals 180. Down here we'll get 17, and that's approximately 10.58, so I'll round to 10.6. So I'll write that down here. It's about 10.6 flies per day. Now we can see what's happening, kind of what we thought would happen. We can clearly tell that as we're getting closer to point P, the rate of change in the number of flies is starting to increase. Let's move Q even closer. All right, I'm continuing the table down here. This is Q and the slope of PQ. I'm just continuing the Q column here, just for lack of space, and then the slope of PQ column here. So this is just my next Q. I've graphed it here at, let's see, let's guesstimate a little bit, 30 comma, I don't know, let's say 260. That's good. And I'm being kind of cavalier about the values I'm picking because the exact value is not as important as the general idea. Okay, let's draw the secant line between this P value and this new orange Q. All right, we can clearly see that this secant line right here is much steeper, so its slope should be greater than 10.6. So I'm going to do the work right here to find the slope of this new PQ. I'm going to do the work right here in orange. And I'm going to take our second y value, which is 260, subtract the y value of P, which is 150. Again, I'm just finding slope. Y minus y over x minus x. So I did the y coordinate minus the y coordinate. Now I'm going to do the x coordinate, 30, minus the x coordinate of 23. All right. Okay, so we're going to end up getting 110 over 7, and that is approximately 15.71, so we'll say 15.7. I'm just rounding to the nearest tenth. So this is 15.7, and this is like a real life example, so I'm using the units flies per day, much steeper. Let's move Q even closer to P. All right, this new neon green Q is pretty close. It's gonna be the last one we do actually. So it's at day 25, and it looks like it's about 190-ish. It's pretty close to 200, so we'll call that one 25, 190. And let's go ahead and find the slope of that. Let's draw the secant line first, actually. All right, a much steeper line we can see is in green. Let's go ahead and find the slope there. So I'm going to do 190 minus 150, y minus y, over 25 minus 23. So that gives us 40 divided by 2. This one's easy, no calculator necessary. All right, so this one is 20 flies per day. Now it's going to be harder to get closer and closer just because of, the capabilities of getting so much closer, and it already looks a little crowded. The idea is that we eventually get Q so close to P that their distance here is negligible, meaning the distance between the two x values is extremely small. Essentially, the distance between P and Q becomes nothing. And as you can see, that's an issue because we're dividing by 0. So that's why calculus comes into play to save the day. And when we no longer have a secant line anymore, we have, once Q gets so close to P that Q doesn't really exist anymore, and we're just drawing this line through P, we essentially have a line that's only going to hit our function at one point. That's called a tangent line. So a secant line is all these lines here. These are all examples of secant lines, these 4, because they hit our function or curve at 2 distinct points on the curve. A tangent line, which we will see shortly, is one that only hits at one point, and that's how we find the exact or instantaneous rate of change at a point. See, we're estimating it pretty well. We can clearly see that our average rate of change was not a really good estimate at how the population of flies changes on day 23 at point P. But as we got closer and closer, we were able to see that it looks like our fly population changes closer to about 20 flies per day at point P. That is the idea of calculus, finding how our function is changing at an exact point. On this slide here, I have a xy axes, and I have a function f of x just graphed in blue. I do have the coordinate point a, comma, f of a here in pink. These dashed lines are just showing the x and y coordinate. And this orange line right here is an example of a tangent line. A tangent line is a line that hits our function only once. The slope of this tangent line represents the instantaneous rate of change of the function. It's representing the slope of the curve meaning function. It's representing the slope of the curve at that exact point when x equals a. In this case, when x equals a. So the slope of the tangent line is the instantaneous rate of change at that point. Instantaneous meaning at that instant. The slope of the tangent line is denoted as m for slope sub tan. Just like the slope of the secant line was m sub sec, m sub secant, the slope of the tangent line is denoted as m tan, or m sub tangent. Now, how, using calculus, can we find the slope of this line? We know that in order to find the slope of a line, you need 2 points. That's the issue with this and why we need calculus. We only have 1 point. What's another point? Well, we saw before in our fruit fly example that we took point Q closer and closer and closer to point P, and if we kept going, basically the distance between them would be negligible. Let's talk about this using calculus. Let's say we have some other point here, and I'm going to call this distance between these 2 points. This distance is going to be h units. So this coordinate point right here is going to be called a plus h, because the distance in between these 2 points is h. Then that coordinate point would have a corresponding y value of f of a plus h, because that would be its corresponding y value, f of a plus h. Now, the idea that we explored before is that this coordinate point here gets closer and closer and closer and closer so that h goes to 0, right? The distance between these 2 points will go to 0, and then basically we can find the slope using those 2 points as this point basically becomes this one. So this coordinate point, a plus h, is going to get closer and closer to a because h will get smaller and smaller. That's the idea. And how do we find the slope between 2 points? Well, we use the slope formula. So let's use the slope formula. So I'm going to write this off to the side here. We're going to find the slope between these 2 coordinate points first. Then we'll address the issue of h basically going to 0 as this point gets infinitely closer to the pink point A. Let's write that out. So we'll do the y coordinate f of a plus h minus the other y coordinate f of a, all divided by a plus h, the x coordinate, minus a, the other x coordinate. Now, what happens to this denominator? The a and the minus a end up canceling out, so we're left with only h down here. Now, once again, this is a very pre-calculus way to look at it. We're not really just finding the slope between these 2 points. That would be the average rate of change slope of the secant line. I want the slope of this orange tangent line here. I want a plus h, this coordinate point, getting closer and closer to this one, which is hard to show on here, I will say. But I want h to go to 0, the distance between these 2 points to go to 0. We know that that is a limit in calculus. So in front of this, I'm going to put the limit as h approaches 0. That's where calculus comes into play. So this right here, this is the slope of the tangent line, or the instantaneous slope of the curve at x equals a. This is the slope of the tangent line at x equals a. It is the instantaneous rate of change, the slope of the curve at exactly that point. That's why we need limits. That's where calculus comes into play. It's how our function changes at an exact point. In the previous video, we took a look at the function x squared minus x, and we found the average rate of change between when x was -3 and when x was 0. Now we want to find an instantaneous rate of change using calculus. We want to find the slope of the curve at exactly when x equals -3. So we are going to use our formula that we just found and find that instantaneous rate of change. So in this case, our a value is -3. That is the exact point that we want. So we are going to find the limit as h approaches 0 of f of negative 3 plus h minus f of negative 3 all over h. All right, now this looks complex, but it really is just algebra. So we're going to find the limit as h goes to 0. And then I put this part in orange here. I'm going to plug in negative 3 plus h into our function. So I'm going to do that in orange right here. So we're going to have negative 3 plus h squared minus negative 3 plus h. So that's just this part. I found f of negative 3 plus h, meaning I plug in negative 3 plus h into our function here. It gets squared minus plug it in here. Then I'm going to subtract f of negative 3. And I'm going to put that in parentheses because I'm subtracting. So I'm first going to square negative 3 and then subtract it. So I'm going to square negative 3 and then subtract negative 3. So this is f of negative 3. I just plugged it in. All over h. So in our next line, we'll have the limit as h approaches 0. Then here, I'm going to square negative 3 plus h. That means negative 3 plus h times negative 3 plus h. I'm going to do that off to the side here. Squaring something means multiplying it by itself, so we're going to FOIL this out. We'll do negative 3 times negative 3. We'll do negative 3 times h. We'll do h times negative 3, and we'll do h times h. Combining those two negative 3 h's, we'll get 9. 9 minus 6h plus h squared. Then I need to distribute this negative sign through, so we'll get plus 3 minus h. Then I'm going to figure out what one number this is inside here. So this is 9 plus 3. So that's a minus 12 there at the end. All over h. And as we know, 0 over 0 is indeterminate form, and that's an issue. So I'm factoring. I'm factoring the greatest common factor out of the numerator. Then our h over h can end up canceling. So we're left with the limit as h goes to 0 of negative 7 plus h. I now can use direct substitution, and I'll get negative 7 plus 0, which is negative 7. Now, what does that mean? It means that this function here, x squared minus x, this is the coordinate point negative 3, 12. So when x is negative 3, take a look here. Our function is decreasing rapidly. If we were to draw the tangent line here, and I'll put it in just a second, that tangent line would have a slope of negative 7. On this function, our instantaneous rate of change, the slope of the curve at exactly when x is negative 3, right here, that slope, the way it's changing, is negative 7. So our function's decreasing rapidly here. So because it's decreasing so rapidly, I actually graphed the tangent line here, and it is hard to see. This tangent line only touches at one point, negative 312, right around here. And if we were to hone in on it a little bit, it is difficult to see, but it does touch right there. And as you can see, this tangent line, it touches one time and it has a slope of negative 7. Next time that we touch on 2.4, so in our next class, we will actually talk about getting the exact equation of the tangent line. But for now, all we need to do is find that instantaneous slope. Here is the moral of the story today. So just make sure you have this information in your notes. Thanks for going through all that. I know it was a long video, but this is a really important idea in calculus. So I really want to make sure that you understand the idea behind secant and tangent lines.